Okay, today we're going to have a look at simple proofs involving numbers. So we can prove simple results using what we call direct proofs or simple proofs involving numbers, rather than something like mathematical induction. Now, often these results can be proved by induction, but these proofs are much quicker and simpler. Now, obviously, we can never prove something using just one case, but we can disprove using one case, so that's something important when we look at disproofs and counterexamples. So, example number 1, if m is odd and n is even, prove mn is even. So, when we have these questions with even or odd numbers, the best thing to do is go, let m equal 2k plus 1. Now we know if you multiply any number by 2, you get an even number. So if you add 1, you have to get an odd number. And we might say that n is 2j for some even number, or some integer j, multiply it by 2, you get an even number. And we might say j and k belong to the integers. Now officially these symbols don't show up in the course, however I believe it is fine to use them, but you could put it in words and just say j and k are integers, or you could even say j and k are integral, which means that they're integers. So let's look at the product mn. Well, it's going to be 2j times by 2k plus 1, which is 4jk, jk rolling, 4jk plus 2j, which is 2jk plus j, which is even. And we're done, QED. The reason I love this topic is because we can end all of the time in my favourite statement, QED. Example 2, we've got if m is a multiple of 3, prove m squared is a multiple of 9. So these are what we simple proofs involving numbers. They're simple. We're just going to let m be some letter. So we're going to say m is a multiple of 3. Any multiple of 3 has to be 3 times by some integer, where k is an integer. So let's look at m squared. M squared is 3k squared, which is 9k squared, which is a multiple of 9. Example 3. Prove that the sum of any two consecutive numbers is odd. So let's say we've got two numbers. K and k plus 1 for some integer k. Well, the sum would be k plus 1. We might say let the sum equal s, and that's equal to 2k plus 1, which is odd. So again, we're not over complicating these questions. We're just going to let it equal to some expression that's always odd or always a consecutive number, adding them together, and hopefully it figures out what we're trying to prove. This case it does. So yeah, we can call these direct proofs. So often it won't tell you what to do. So often in extension 2 we're not going to be told to use induction, we're not going to be told to use direct proof, we're not going to be told to use contraposition or counterexample or contradiction. These are all the proof methods we're going to learn. It's just going to say prove, and you've got to determine which method of proof is the best. So use a direct proof to prove that if a number is odd, then its square is also odd. So let's say let p equal an odd number. Always, an odd number is always 2 times something plus 1. So for some integer k. Let's square it. P squared is 2k plus 1 squared, which is 4k squared plus 4k plus 1. Now we can factor 2k actually. We might just factor out 2, and we can say this is 2k squared plus 2k plus 1. But since k is an integer, we could say this is equal to 2, what's after k, Hij,k,l, 2l plus 1, where l is an integer. Which is odd. Because 2k squared plus 2k is an integer. Okay, example number 5. We've got to prove that if a plus b is 2, we're proving that a squared plus 2b is equal to b squared plus 2a. One of the most useful strategies in this case, and also proofs involving inequalities, is getting the left-hand side and subtracting the right-hand side. In this case, if we prove that the left-hand side minus the right-hand side is 0, then we've proven what has been asked, because you can plus the right-hand side back over and get to our original proof. So the left-hand side minus the right-hand side is going to be equal to a squared plus 2b minus b squared minus 2a, which is a squared minus b squared plus 2a minus 2b. Now that's a difference of 2 squareds there, a minus b, a plus b. And then we can take out a factor of 2 and we get a minus b. Now we can group in pairs. We're going to have a minus b brackets a plus b plus 2. Now we're told, I feel like I've done something wrong there. That should be an a minus b. What's gone wrong there? Yeah, there should be, pardon me, there should be a minus here, I think. Take out a factor of 2, minus a minus b, 2b. Yeah, sorry, this should be a 2b minus 2a. And then this is going to make that a minus a minus b. So then this will make this a minus 2. Right, that's better. So all the mistake I'd made there is I had just written the 2a here, but we can actually see it's minus 2a. Now we're told that a plus b is 2, so this here is equal to 2. So this is equal to a minus b bracket 2 minus 2, which is 0. So therefore, a squared minus b squared plus 2b minus 2a is equal to 0. So therefore, a squared plus 2b is equal to b squared plus 2a, which is what we're asked to prove. Alright, thanks for listening. That is simple proofs involving numbers.